Also, let me. Okay. Feel free to jump in at any point with questions. So today we're gonna figure out what's up with probability. And so we're gonna learn the language of it. We're gonna learn how to calculate probabilities and interpret the results. And we're gonna look at the difference between theoretical and empirical probabilities, and just kind of how that functions out there in the world. Probability started because some mathematicians were looking at gambling. And there's some famous letters between these two mathematicians talking about the mathematics of chance. And that's what probability is. Chance. So if you go to a casino and play any of those games of chance, there is probability governing or kind of behind all the actions. It's how people who own casinos and operate them calculate how to make money and what odds they should put out there and all that stuff. And just so you know, casinos or the way probabilities work and the way casinos are set up is that you lose your money and they make money. And I don't know, unless you're lucky, I guess, have some sort of charm. So one of the words that goes with this stuff is likelihood. That's what probability is a measurement of. So let's get down to, I don't know what page this is in the book. Hopefully you'll have found it. We're going to first define probability. So the probability of something occurring is a number, that's important, that represents how likely it is to occur. I kind of don't like that. I mean, it works. Let's talk about the numerical forms first. So probability is always a number between 0 and 1. And in the middle, halfway, of course, is 0.5. So what corresponds to 1, we can write these as percentages. What we say is 1 is certain, that's the language we use, and 0 is impossible, and 50% is equally likely. So anything above 50% is more likely. If you're a gambling person, that's when you would bet, because when you're above 50%, that means your chances of winning, you're more likely to win than to lose. That's what you want to bet on. Anything below 50% chance means you're less likely. So that's when you don't want to bet. What's interesting about this, to me, is probability as a study of mathematics. It grew out of those games of chance and gambling and that mess. And then it turns out it just shows up in all other kinds of different places and has really practical uses. So we use it in statistics a lot. It's used in physics and quantum mechanics, and there's all kinds of really applicable places where probability is used. And just to be clear, what we're going to study here is the real basic, real surface level of probability. You can go very deep with this stuff. So it's the chance of something occurring, but we need to be a little more specific about that because we can't just a probability is a numerical measurement when we have clearly defined outcomes that we can do calculations with. So it turns out that rain, the probability of rain, which in this case, one way we would write it would look like this: probability of rain equals 0.7. Weather uses probabilistic modeling, and it uses data, and just we have reams and reams of data from years and years of observation. And meteorologists are really good at predicting the weather in the short term. Like weather is highly predictable. Like tomorrow's weather is really easy to predict. What gets challenging is when we get out like a week from today or a month from today or a year from today. Predicting that weather is much more difficult to be accurate, right? we can say it's likely to be cold in November and it's likely to be like what 20 degrees Fahrenheit a year from now because it's typically cold in this area. But things can happen that can change that. Okay, so what comes along with probability is usually we do well. So first, we're going to kind of talk about the games of chance. So processes, we call this, such as flipping a coin, rolling dice, drawing cards from a deck that's carefully shuffled. We call these types of things probability experiments. And it's really just a process that has, he calls these well-defined results, meaning we know what all of the outcomes are. We know what all the possibilities are. So when you think of a deck of playing cards, there's 52 cards in there. There's 4 different suits. There's 2 different colors. There's 4 queens, 4 jacks, 4 kings. We know all of that stuff is in there. And then if we shuffle it up, make it randomly, so we don't know what order the card's in, and we pick the first card up and look at it, we can talk about the probability of what card we will get. Like there's a 50% chance that when we pick up a card, it will be red because half the cards in that deck are red, half the cards are black. And what that leads us to is a definition of what's called the sample space. So the sample space is the collection of all possible things that can happen in our experiment. We often write a sample space like this with little curly brackets, and then we list those outcomes in between there. So if a stoplight were a probability experiment and the stoplight showed colors randomly, which would be super dangerous. So if the light changed by some sort of random process, the sample space of possible outcomes is you could have a green light, you could have a red light, or you could have a yellow light. And you can imagine if this occurred randomly, the light randomly turned yellow from red, or randomly turned green from yellow, or whatever, it would be, it would cause chaos. And so they are really, I actually don't know how lights work, but they seem to be timed and very specific. I do know, right? We do know because green, yellow, red, green, yellow, red. But in terms of when does it change from green to yellow, how much time does that take? I don't quite know how they set that up. Okay, so what I would like you to do is list out the sample space for if we were randomly selecting a student's grade in a chemistry course. And what I want you to do, I had a professor, one of my colleagues tell me about this, in chat. Click the chat button, and there's this little this little thing that says 2, and currently it should say everyone. Click that little menu and select my name, and I want you to type in there your answer. And what that does is it sends the answer anonymously to me, so no one needs to know if you got it right or wrong, and then we'll talk about it together. And then I know kind of where you're all at, and we can talk about the different, if we're running into problems. So I want you to write the sample space for the probability experiment of randomly selecting a student's grade. And you can use letters. Let's ignore minuses if we're using letters, or you can use what JC uses, the 4.0, 2.0 scale. Let me give you 3 minutes to think about that. So the timer for 3 minutes. And then just type your answer in chat. Okay, I got 2 out of 4 responses. Let's look at it. Here we go. 3 out of 5. So, interesting concept here. I agree with different. There were essentially three different answers. If we went with the ABC letter scoring, we might state it like this: A, B, C, D, F. So that could work. Or we could do 0, 1, 2, 3, 4. That would work if I notice I flipped the order around, right? I put in numerical order. We could also look at so the grade. It's a weird thing. Like you all get a percentage, and from that percentage, we determine your grade, right? So it is true that in the class you could have 0% up to 100%, and then those numbers correspond to a particular grade. We could also like throw in here A minus, B minus, C minus. Jackson College actually has a D minus in there, sort of, because it's like 0, there's a 0.5, there's a 1.5, a 2.5, and a 3.5. So we could add in all those things if we needed to. That whether or not we wanted to include all that information would be dependent on the context. So I would like you then one more time, give me the sample space for rolling a 6-sided die. I'm just going to give you 1 minute. What's the sample space for rolling a 6-sided die? We need that. That's not the answer for number 3. But it is, I'll just put SS 6-sided die. Yeah, okay. I'll wait, give you all, let me set a timer for 1 minute. Nice. Okay. Those of you that aren't responding, that's okay. I'm just hoping, I'm assuming either you're just kind of logged in and aren't really able to respond, or I don't know. As long as those of you who aren't responding know what or understand what's going on, great. Okay, there we go. Right. So when you're rolling a 6-sided die, the sample space is the 6 outcomes. Okay. So notice now what we're going to do is we're going to define what's called an event, which is a collection of one or more of the outcomes from the sample space. And what's weird is an event could include all of the outcomes in a sample space. So send me a chat. Send in the chat. By the way, I'm so happy for you to send me wrong answers. That's why I'm having you do it anonymously so that you don't have to feel embarrassed if you are wrong. Yeah. So write the list. Give me the list of outcomes for rolling one die that are odd. Okay. So give me the sample space for this particular definition, which is called an event. And I just love that you all give me feedback. And this professor's like, have them send it to you anonymously. Then you get it all. I love it. Nice. Okay. So I need to make sure I give you time to write. There we go. Love it. Okay. 1, 3, and 5 are all the odd numbers in this sample space. So that's an event. Okay, so let's move on then, and we'll figure out how to do how to calculate that probability in a second. Now, our author suggests there's a difference between an outcome and an event, and there is. Each one of these items inside this sample space is an outcome. These three items together, these three outcomes together are the sample space of this event getting something that's odd. So an outcome can only ever be one thing, whereas an event is either one outcome or a list of a bunch of outcomes. That's really the only distinction between the two. And it really, to me, isn't important that you know the difference between whether you correctly define something as an outcome or an event. So I want you to write a sample space. Get ready. This is tricky. Type it to me in chat. Give me the sample space of flipping 2 coins. What are all the possible outcomes? So you flip the coin and you record the result heads. You flip it a second time, you record the result, it's tails. So one outcome is heads and tails. So give me the sample space for flipping 2 coins. And I'll give you one of them. Like, this is how I would write it. Heads, heads. That's one option as an outcome. So let me pause myself and type that in chat. Set a timer for 1 minute. Nice. Nice, y'all. Excellent. Right? So 2 heads, 2 tails, heads or tails, tails or heads. I like that you all just instinctively wrote these as different outcomes. The order you write these doesn't matter at all, by the way. But first getting heads, then tails, second getting heads, first getting tails, then heads are treated as different outcomes. But they could look the same. All right, so now we're saying how many results match getting heads on the first flip and tails on the second? What's your all's answers? Here we're counting how many times can that occur? First we flip heads, then we flip tails. Yeah, tricky, right? That's a tricky one. Let me circle the outcome that corresponds to what this guy just said. Getting heads on the first flip, tails on the second, it's this outcome, and there's only one. Now he says that's an outcome. Well, what if we said, what's the probability of getting heads first, tails second? That's an event. Right? So I don't like what he does here, but there is only one outcome. All right. So for number 2, how many results match getting 1 head and 1 tail? And let me add to that, list them. Good, 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 y'all. Okay. Y'all killing it. So there's 2, and it's heads, tails, tails, heads, or any order of that. Excellent. He calls that an event. It's true when you have more than one outcome as a possibility. It's definitely not an outcome that we would call that an event. I'm going to skip these next 3 because I don't want to mess with those. I'm going to jump down here. And let's do the did you get it problem. So a baseball team has 12 pitchers on the roster. The manager who's intent on losing his job, decides to pick the starting pitcher for tonight's game randomly. What is the sample space? Okay. Write an example of an outcome, an example of an event. Don't do that. Write a sentence of what the sample space is. Let me tell you that. Okay, there we go. Yeah, I like that, Jennifer. Let's name them numbers. Let's numerically name these pitchers, and let's get the sample space. So pitcher one, etc. Maybe this is, I don't know. I don't know what you'll think. Is this confusing? It would just look like this. I'm sorry. We might actually attach names to these. We would attach names to these, and we would do 1 through 12. Excellent. Yes. And we put them in the squiggly brackets to show here's the, that's actually set notation. So let's get then to how do we calculate a probability with these. I'm going to come back to this problem, and we're going to calculate some probabilities with it. So first, we're going to look at what's called theoretical probability. Key word there, if you're not super familiar with the word theoretical, is we're basing things off of theory, which in the probability world means we know all the outcomes. We know all possible outcomes. Know all possible outcomes. So what we do is we figure out all the things in the sample space, and then we figure out the number of outcomes in a particular event, and we divide the number of outcomes in the event by the number of outcomes in the sample space, and we've calculated a theoretical probability. So let's say we're flipping a coin 100 times. How many times do you think the coin would land tails, side up? I'm going to write out the sample space for this probability experiment. There's just two outcomes, heads or tails. And so tell me, how many times do you think, if you're flipping 100 times, how many times do you think it's going to land on tails? Nice. Okay. I've got people saying 50 or half the time. Yeah, right. So if theoretically there's only two outcomes, and if they're equally likely and we're just flipping, half would be tails, half would be heads, most likely. What percent is that? Well, you said it, 50%. What fraction is that? Well, if it's 50 out of 100, that would be this, which would reduce to 1/2. Right. So that's the kind of the structure of probability. These are the three possible representations of probability. Actually, these are only two of them. The third is decimal, 0.5. Okay. So let's give you a little formula. This is kind of a reference sheet idea. When we're calculating theoretical probability, we take the number of outcomes in our event, which we call capital E, whatever that is, and we divide that by the number of outcomes in the sample space. Remember, sample space here is all possible outcomes. So that's the total possible. And then the event could be any amount of outcomes from the sample space. So at a maximum, the event could have the same amount of outcomes as the sample space. Then it would have a 100% chance of happening. So let's go back here, and I want you to calculate the probability of randomly selecting a pitcher numbered less than 5. All right. So note the notation is we put this P with parentheses. This is not function notation. This symbol, this P, tells us here comes a probability. What's inside here is the event. And then this is often equal to, we do some sort of fraction. So, or a decimal or a percent. So your job here is to tell me what's the probability our baseball manager randomly selects a pitcher who has a number less than 5. I'm going to give you 2 minutes. Set a timer for 2 minutes. And then get some more water while you chat that to me. Okay, I got 2 answers out of 4. 10 seconds left for those of you who haven't answered to register your results. Oh, okay, there it is. So first thing to note, the way this probably works is we want the number of outcomes in the sample space and then the number of outcomes in the event E. So there are 12 pitchers. That's the sample size. That's your denominator. The question is, how many numbers are less than 5 in our sample space? So I'll list the outcomes that are less than 5 for event E. It's 1, 2, 3, and 4, which means our fraction is 4 out of 12. So just be careful with the word less than. It doesn't include the 5. There are other languages, other words that will make it. Yeah, no worries if you got that wrong. It's probability is a really picky with language. You have to be very careful. So this, if we wanted to simplify this fraction, we could write it as 1/3. If we wanted to turn that into a decimal or a percent, we could take the 1 and divide it by the 3, and we get the 33%. So this is approximately 0.33, which is 33%. So those are all different ways to write out that probability. Okay, let's do another one. Here we're rolling a single 6-sided die, and we've got 3 probabilities to calculate. In some ways, these are a little simpler than the other ones. So just answer all three of these and then type your answers in the chat. I'm going to write out the sample space as a starter here. And you all figure out those three probabilities. Let me give you 2 minutes. Let me give you 3 minutes to think about that. I don't want to rush your work. Okay, I've got everyone's answers. Excellent. So yes, 1 out of 6. There's only one outcome in that event. Ooh, let me make sure this stops. Oh, it did stop. Okay, so 1 out of 6. There's only one outcome in there. That's a 2. That's this one. Number less than 5. There's 4 of those, so that's 4 out of 6, or 2/3. And ruling an odd number, there's 3 out of 6, or 1/2. Excellent. That's the essentials of probability, right? That you can figure out how many outcomes are in the event divided by how many outcomes are in the sample space. That's like the core of it. Figuring out those two numbers can, in some cases, be the most complicated part. But we stay kind of straightforward. So what now if we flipped 3 coins? So let me give you a chance to write the sample space. I'll give you one of the outcomes. I'll give you like 3 minutes to work through this. Maybe I'll pause myself for 3 minutes. And if no one's answered, I'll keep waiting until someone answers. So if we're flipping 3 coins, one outcome could be heads, heads, heads. Find the others. I'll give you a hint. There's 8 total outcomes. Set a timer for 3 minutes. Man, you all crushed it. Love it. Okay. Turn off the timer. So there's our sample space. Heads, heads. I'll write out what y'all had. Heads, heads, tails, heads, tails, heads, tails, heads, heads, tails, tails, heads, tails, heads, tails. 1, 2, 3, 4, 5, 6. Oh, I'm missing heads, tails, tails, and then tails, tails, heads. Okay. So there's our sample space. So now we're going to use that to calculate these 3 probabilities. So let me give you another 3 minutes on this. Okay, same thing. Hopefully there's enough time, or maybe there's not enough time. We'll see. We'll see how it goes. Write your answers once you have them. Set a timer for 3 minutes. Okay, nice, y'all. Turn off the timer. Okay, so two tails. We're looking at the key question. It looks like y'all answered it. Is how many have just two tails, right? So 1, 2, 3, and you'll crushed it. 3 out of 8, and that could be a decimal or percent. All up to you. At least one tail. Okay, so at least one tail. We've got 1, 2, 3, 4, 5, 6, 7. Now that might, let's see, did that get any of you? No, good job, y'all. They didn't get anyone. At least one means this is the same thing as one or more. So there was only one outcome that didn't fit this. That's 7 out of 8. At most one means one or less. So we can't have more than one in here. And so we go through, erase all these. So it's heads, heads, heads. That's 0 tails in it. And then 1, 2, 3, there's 4. So this one's 4 out of 8. Now, did that get you all? I think that got you all. Yeah. So at most one tail could mean one or none, really. So we don't need to say less here because there isn't anything less than 0. One or none. Does that make sense, y'all? That inclusion of the heads, heads, heads meets the criteria of at most one tail? Because I think all of you missed that particular one. And this language is tricky, at most and at least. Okay, good. So far these are still examples of theoretical probability because when we flip 3 coins, we can list out all the sample space from the get-go, and we know exactly, we know theoretically what should happen. There is an assumption we're making here. We're making that these coins are called fair coins. And fair means they're unweighted. So it's equally likely, when we flip it, it's equally likely to land on either side. There are like trick coins or whatever, where when you flip it, it's more likely to land on a particular side because it's weighted for that side to fall. Okay. So let's glance here at a couple properties. You're never going to have a value greater than 1 or less than 0. He's got a description of why here. Part of it is because the maximum number we could have is when these two are equal. So the events in the number of outcomes in event E can only be a maximum equal to the sample space. That's when you would get it equal to 1. And you can never have a negative amount of things. That's why we can't be below 0. And then 0 just means it can't occur. There are no outcomes in the event that are also in the sample space. And then the other one is if we take the probability of each outcome in the sample space and add it together, we get the probability of 1. So this is kind of what I already put together for you. Impossible is 0, 50-50, equally likely is the words I would put in here. Equally likely. And then more likely and less likely. So he uses the language likely and unlikely, which I think works as well. So we can estimate these probabilities. The chance of you passing this course, you can guess. You say, yeah, there's a 100% chance because I do all my work and I know, that's going to happen. Living past the age of 100, you could base this off of data, like how many people actually live over the age of 100, and then you could try to live the same lifestyle those people lived, although there's genetics that goes into there. Winning $1 million lottery is 0% chance. I'm going to tell you that right now. Well, no, $1 million lottery is a little higher than 0. doing tonight's homework. These are all what we would call subjective probabilities. We're kind of just making a guess at it based on some sort of knowledge. But there are other types of ways, there are other types of probabilities that we're building up to, and that is what's called empirical probabilities. But first, let's look at a special definition. And that is sometimes we want to know the chance that an event will not occur. Like the probability of rolling a 2. What's the probability of rolling a 2 with one die? What's the probability that would not occur? So we know the probability of rolling a 2 with one die, we already did that above, was 1 out of 6. And then we're like, well, what's the probability of not rolling a 2? Well, that would be all the other options. And if you think about how many other options there are, there's 5 of them. And there's only, so 5 of the values are not 2. So that means there's a 5 in 6 chance. If you look at this probability and think about the reality, what we're doing is we're taking all 6 options and subtracting all the ones that are not the 2, and we get the 1 out of 6. I think this is a little weird how he's doing this. The point is, when we talk about not, we're talking about a compliment, not a like you look nice today kind of compliment. It means all the other events that are not the particular event we're talking about. So we can define an event in a sample space, and then the complement of that event is all the other events that aren't used in it. There's a different notations. We can write it like E prime or E complement, and in words that means not E. So is this super useful? I don't know. Let's skip down here. Here's a nice little formula where it is sometimes useful. So if we have the probability of an event is known, then the complement, the chance of that event, or the complement of that event happening, is just 1 minus the probability of event. This also means that we can take the probability of an event and calculate it using the complement if we knew it. 1 minus the probability of the complement also gives us the probability of the event. Or put another way, add the probability of the event and its complement together and we get 1. So how does this work? Well, here's an example. We've got 32 trials on the docket in a county court. So 5 are homicides, 12 are drug offenses, 6 are assaults, and 9 are property crimes. So that's the sample space of those 32 things. We're being told what each one is. So if jurors are assigned to trials randomly, what's the probability that a given juror won't get a homicide case? Let me give you 5 minutes to think about that and see if you can't get the calculation. So dump your answer in chat once you figured it out. Set a timer for 5 minutes. Okay, sorry, I got too into what I was doing. Awesome. So what you could have done, right? It looks like what you did is took 32 and added together 12, the 6, and the 9. So what? That's 30, 27 out of 32. The other method, right? So this is just a direct calculation. The probability of not assault. So it's the probability. The other three is we'd add those two together, or we could say, hey, 32 minus 5. In other words, we're going to look at the probability of homicides is equal to 5 out of 32. And so the probability of not homicides, just say not H, is equal to 1 minus that 5 over 32, which is 27 out of 32. This is a convenience thing, the complement. And in these examples, I don't know, like these probabilities and the probabilities in this class that you calculate are not really complicated enough to need for the complement to be super helpful, in my opinion. But there are some that are there are some calculations where it's quite helpful. One of the things I do want you to note is, or that I do want you to know, is what that complement means, like how it's defined and how it's put together. Okay, so let's jump into what's called an empirical probability. So empirical probabilities, we use data. Oftentimes, what this is we can't, it's not an experiment. We don't know all the outcomes at the beginning. And so we use a data set to help us figure out, to calculate probabilities. For example, when Jackson College designs the courses or plans the schedule for courses we're going to offer the next semester, we look at how many students, like for spring, this next coming semester after Christmas break, which is the spring semester, we look at how many students are currently enrolled at Jackson College in the fall semester, what classes are they likely to take, and then we build our course schedule off of that. Or we use data from like how many students are graduating from high school and how likely are those to come to college. So how many sections of a particular course do we need to build as a beginning? That's an empirical probability, and we're using that based on a data set. So our author says here it's observed frequencies. We can actually take theoretical probabilities and do, or we can do empirical probabilities with theoretical stuff. So like we could flip a coin 10 times, record the results, and create a table off of that and calculate probabilities using that data set. So we could look at, hey, theoretically what's happening, or theoretically we expect 1 in 2 chance for tails to land heads up. And then here we did an experiment. We've got a data set, and 6 out of the 10 times it landed on tails. Okay, so on any given day, there are exactly 2 possibilities. You can go to the gym or not go to the gym. Why would this fact and theoretical probability not be useful in deciding the probability you go to the gym? I don't know. Probably because your decision to go to the gym is based on how you're feeling that day, not on a random process of selecting to go or not to go, right? So maybe you ate a super heavy meal and you feel more like falling asleep, or maybe you didn't get any sleep last night, or blah, blah, blah. So there's lots of other factors that would go into, say, you choosing to go to the gym. However, if we looked at last month's data set, and let's say 10 out of 12 times you went to the gym, you could calculate your probability as a 10 in 12 chance of going based on your previous behavior. That's what we mean by empirical probability. So the author points out, he's already done what I've done here. If you flip a paper or plastic cup, it can land on its top, its bottom, or its side. Are these outcomes equally likely? What do y'all think? I don't even have a paper cup, so I can't do this. Yeah, I'm gonna say no. I don't know. What do you think? Probably the cup, like the cup is gonna be dependent on how you throw it, and then how it lands on the surface and what surface you're landing on. So probably, so let's make the sample space here. Yeah, I would agree with that. So the sample space will say T for top, S for side, and B for bottom. These are the three outcomes. Okay, right. So apparently there's a game called Flip Cup. Um, and I like that. The side has more surface space, so that would make sense for that to be more likely to occur. So suggest to me, what's the probability it lands on its top? What's the probability it lands on its side? And what's the probability it lands on its bottom? What would we guess? Um, and here's the thing: the key to this to estimating these is that when we add the three together, they have to add up to 100 or one. So if we say the top, or if we say the side is most likely, let's say it's going to land on its side 50% of the time. And then I'm going to say the top is usually like wider, right? So I would make that a little bit higher. Let's say that's 30% of the time. And then the bottom 20% of the time. Like that would be my guess. Maybe that's totally wrong, but we could get some cups and test it. So what we would do is flip cups 100 times, record how many times it landed on any one of these things, and then we would calculate each of these percentages, and that would be an empirical probability. So the formula becomes a little different. It's like the frequency of the event. So how many times did it land on a particular side divided by the number of times we performed the trial. So if we flip the cup 100 times, the denominator would be 100. And then the frequency would be how many times it was top, side, or bottom, right? So we're not going to do this because we don't have it. And we're going to skip that one. And we're going to do this one. So number 17, we got a random sample of 500 people. That's the sum. Think back to, oh no, that's coming up. We're going to put this little symbol here. This is 500. We have type O, type A, type B, and type AB. I'm going to fill in this table. O has 223 people in there. Nope, I'm wrong. That's 210. 210, 223, 51, and 16. So calculate for me the probability of type O, the probability of type A, and let's just leave it at that. We'll just do those two. Oh, what nice, neat numbers. Love it, y'all. Good. So empirical probability here, we take the total, the frequency, divide it by the total. This one happens to be exactly 42.42 or 42%. This is 223 out of 500, which is 0.446 or 44.6%. Rounding that to 45% is totally acceptable as well. Excellent, y'all. Good. That's empirical probabilities. So let's try this problem. So here we got the same data set. And we're going to get a little, I don't know if anyone's going into nursing here. So when a blood transfusion is needed in an emergency medical situation, you might think you'd have to receive the same blood type as your own, but that's not true. O is the universal donor. It can go to anyone. A can go to A and AB. B can go to B and AB. And then the poor AB person can only go to AB. So we're going to use this chart and our data here to calculate the probability that a randomly selected patient can receive only one type of blood. Ooh, this is a tricky one. All right. I'm going to give you like 3 minutes to answer 18 and 19. So make sure you're using these numbers in your calculation. You're using using the empirical data. All right, let's talk about these. So it's a tricky problem. I think you all got it. So the probability that a randomly selected patient can receive only one type of blood. What we have to do is look at the recipient side and see which of these blood types can only receive one type of blood, and it's the O patient. So how many patients have type O blood? There's 210 of them out of the 500. Does that make sense? What's the probability variance can only receive one type of blood? So it's these 210 that can only receive one type of blood, and it's the O type. So this is that 42%. So 42% chance that a randomly selected patient can only receive one type of blood. How do you feel about that? Does that make sense to you? Because that's not the answer I think anyone gave. I think that's, oh no, one of you gave. Good job to you that got it right. I get that looking at the 16 out of 500 is reasonable. So that's the only can give. An AB person can only give to one other type of person, and that's an AB blood type. But this was looking at receive only one type of blood. So we're looking at this column. The second one, if an accident victim has type B blood, so we're here, type B, and an EMT on site is the only person willing to donate blood, what's the probability that it will be compatible with the victim? So we have to look at what types of blood can a type B person receive. They can receive type B or type O blood. You all with me on this? So they can receive those two types. So the frequency of people that can donate blood to this type B victim is the type O, which is 210, plus the type B, which is 51, and all that divided by the total number of people in our sample. So that's 261 over 500. How do y'all feel about that? That's 0.522 or 52%. Yeah, good. Good. Any questions on that? This is more like the careful reading. That's really what makes probability tricky, in my opinion, is the reading through and making sure you're understanding which one is which.
Okay. It has to do with like the language of it because it says an EMT on site is the only person willing to donate. So I mean, to me, from my understanding, the 261 or whatever isn't willing to donate. It's one person.
Well, the question here is, you're right. There's only one person, so we're only making one selection out of the 500 possible people.
Okay.
So for some reason, there's 500 people standing around this victim,
Okay.
and or I mean, it's just we're just using this data set as our empirical data. And so the question is, what type of blood does the EMT have?
Okay.
That's what we're worried about. And since we're wondering who can you got it right, who can they go to? They would have to have B or O blood type in order to be able to do the transfusion. All right, two more. I'll give you 3 minutes on these next two. So the timer 3 minutes. Yeah, this is a tricky one, huh? So this person is receiving the blood. They can only receive from type A or type O. So if they're not type A, that means they're type O. So question 20 is this, 210 out of 500. Nice. Good. That's the 42% again. It's like our most favorite answer, apparently. So the second one, what's the probability that random second donor blood can be given to patients of more than just one blood type? So you have to look at, this is the only one that can't be given to more than one type of blood type, is the AB. So we could take the 500, subtract out the 16 people that can only give to one blood type, and we get what, the 484? That feels right. So that probability is 484 out of 500, which I believe is what you all are writing, texting me. Oops. Oops. Which is the 0.968. Does that make sense, everyone? Does anyone have any questions on that? Nice. Good. Or 97% is a reasonable thing. Okay. Let's just real quick check. What do you think? For number 22, the probability of a high school basketball player one day being drafted by an NBA team is this. Do you think that's theoretical or empirical? So here the question is, how was this number calculated? Based off of, is it empirical or theoretical? Was it based off of a data set, or is it based off of knowing all the possible outcomes and just doing that calculation? You all nailed it. I'm seeing that. This is definitely empirical. What they do is they would look at how many boys there are, high school basketball players there are, and then how many have been drafted into the NBA. And I believe it's just LeBron James, and is there one other? Right. So this is based off of a data set. How about 23? Is that theory? Is that theoretical, or is that empirical? The probability of being dealt one pair and 5-card poker. This is definitely theoretical. Good. Because we know all the possible outcomes in a card game. So we know all 52 cards. And so we can perform this calculation just based on that theory. We don't look at the data sets on how often things are dealt. And that actually isn't helpful in reality, because every time we shuffle a card of decks and start dealing, that's a brand new thing. The previous ways things are dealt, it has no effect on the probabilities. Okay, 2 more. The probability of being in a fatal accident if you make 2 car trips a day for 1 year is 1 out of 13,750. It's a tiny chance. This is 0.1, 2, 3, 4, 7, 3. That's a percentage. That's 0.0073%. So there is a 0.0073% chance that you die in a car accident if you make 2 car trips a day for 1 year. And I saw one answer, definitely empirical. They looked at how often has this occurred. So obviously there's lots of people that die in car accidents. It's a pretty common way to die. But if you think about how many times someone is driving in the car, it's just lots and lots of people are in cars lots and lots of times. And more often than not, you don't get in a car wreck. And even more often than that, you don't die, because cars are fairly safe these days. All right, the probability of winning some prize when buying one New York State Lottery scratch-off ticket is 0.216. Theoretical, empirical. Good, good. Yep, this is theoretical. Any lottery ticket, any game of chance, the probabilities are based off of theory, not how many people have won in the past. Okay, y'all, let's do the lesson check before I forget, because you know I'm going to forget. And then I think I'm going to let you all, well, let's do we might as well do the worksheet together. We still got what, 35 minutes? Yes, there was no class last Wednesday. That was Thanksgiving break of last week. And then the week before that, there was no class because I was on a conference. And I think I did a very bad job telling that to everyone. I don't know that anyone would need help answering this lesson check. What percentage of time would you expect the coin to land tails up? 50% would be the answer on that one. Excellent. Okay, so let me pull up the worksheet. And let's look at that 4-1. This is page 44. I'll let you all do 1 and 2 and 3. So let me give you 5 minutes to try it, and then we'll talk about your answers. The timer for 5 minutes. You all are doing it. Yeah, a numerical measurement of the likelihood of an event to occur for number one. Excellent. Possible values for a probability. One way to write it is like this. Come on. 0, 1 with brackets. So any number between 0 and 1, you could also write it like this. Let's go 1, or you can just say any number between 0 and 1, including 0 and 1. Good. And then if you roll a 20-sided die, what's the probability? You roll a 7. There's only one 7 on that die, so that's 1 out of 20, which is a 0.05 or a 5% chance. Those are the 3 different representations of probability. Good. Okay. Let me give you, well, try this next one. You've got 2 minutes and 25 seconds to try the next one. Well, yeah, try it out. There's the link to look up the winning thing in case you can't click it from here. How are we doing on this one? Y'all getting stuck, or is it making sense? So like this is your job, is to select 5 numbers 1 to 69. So I'm going to do 2, 60, 39, 3, and 18, and then a number from 1 to 26, 13. Okay, those are the numbers I selected to win. I told you there are this many possible number combinations that meet this. And I'm suggesting there's only one winning number combination that gets the top winning number, the jackpot winning. So that means my probability of winning is this. Which I think it's important to write that out as a decimal so you really understand your chance of winning the jackpot for the Powerball 8 thing. So there are 8 zeros before this. 1, 2, 3, 4, 5, 6, 7, 8. This is the probability. Let me convert it to a decimal, a percentage. 1, 2, 3, 1, 2, 3, 4, 5, 6. This is my percent chance that my number wins the lottery. So we can all agree I lost, right? Here were the winning numbers for the jackpot. And did I get any of them right? If I had played these numbers, let's see. None of my numbers are correct. So I lost. Surprise. And you can see that no one has won this top winning condition. No one has actually won the top 3 for this particular lottery. And part of the reason, yeah, right. Part of the reason I want to know this, I want to show this to everyone is like, no one, you're never going to win the lottery. You're not going to win. You're not going to win the big money. And I always have students say, well, someone does, right? Because you remember someone did recently, they won, they had that huge $1 billion payout or whatever. Sorry, it's not going to be you. And the reason I can say that is this is the chance that it is you. And I can comfortably say, so far in all my years of teaching at Jackson College, 6 years, none of my students have won the $1 million lottery. And so I've been 100% right in predicting your chances of winning that big one. You're not going to win it. Sorry. Cool. Okay, y'all. Any questions? Anything? Any pressing things for you? Otherwise, that's it for today. And if you haven't gotten your Unit 3 project done, keep working on that. Get that in. Hey, I graded Unit 2 for one of the classes and half of the other classes, and I'm hoping to get that finished. Turns out I did what probably most everyone did and didn't get any work done over Thanksgiving break. But I'm feeling the heat of deadlines like you may be as well. And so I'm going to try to I'm getting there. So anything that you all need.